In the previous episodes, we learned how Kubernetes creates pods and keeps them running using deployments and replica sets, but there is still a problem. How do applications communicate with each other? And how can users access applications running inside the cluster? That's exactly what we'll learn today. Before we jump into the hands-on section, let's quickly look at today's roadmap. First, we'll understand what a Kubernetes service is. Then, we'll see why pods need services and what problems they solve. After that, we'll explore the three most common service types: ClusterIP, NodePort, and LoadBalancer. Next, we'll look at how applications communicate internally inside the cluster. And finally, we'll learn how service discovery allows pods to find services automatically without knowing IP addresses. Let's get started with the most important question. What exactly is a Kubernetes service? Let's start with the problem. Pods are not permanent. Kubernetes can delete and recreate a pod at any time. It might happen because of a deployment, a failure, a node issue, or simply because the application is being updated. When a new pod is created, it receives a new IP address. In this example, pod A had the IP address 10.244.1.10. After being recreated, the new pod receives a completely different IP address, 10.244.2.15. The application is still running, but the network address has changed. Now, imagine another application was trying to connect directly to that pod. As soon as the IP changes, that connection breaks. Applications need a stable way to find and communicate with each other, and that's exactly the problem Kubernetes services solve. I'm going to create a simple Nginx pod and access it directly using its IP address. This command creates a single Nginx pod. Now, let's find its IP address. Let's see if we can reach it directly. I'm creating a temporary pod that contains curl. We'll use it to make requests inside the cluster. The application is responding. We're communicating directly with the pod using its IP address. Now, let's delete the pod. The pod no longer exists. And now, the address no longer works. The application disappeared because the pod disappeared. This is exactly the problem. Pods are not permanent. They can be deleted, recreated, or moved at any time. And every new pod receives a different IP address. If applications depend on pod IPs directly, communication becomes unreliable. So how do applications find each other in Kubernetes? That's exactly the problem Kubernetes services solve. So if pod IPs keep changing, what can provide a stable address for our applications? Let's look at what a Kubernetes service actually is. Now that we understand the problem, let's look at the solution. A Kubernetes service is a stable network endpoint that sits in front of one or more pods. Instead of connecting directly to individual pods, applications connect to the service. The service keeps the same IP address and DNS name, even if the pods behind it are deleted and recreated. Think of it as a permanent front door for your application. Clients don't need to know which pod is running or where it is located. They simply send traffic to the service. Kubernetes then automatically forwards that traffic to one of the healthy pods behind it. In this example, users connect to the service, and the service distributes requests to multiple pods running the application. This gives us stability, reliability, and a consistent way to access our workloads. But if pods can already communicate using IP addresses, why do we actually need services? Let's see what actually happens when traffic reaches a service. Users don't connect directly to individual pods. Instead, they send requests to the service. The service provides a stable virtual IP that remains available even when pods are created, deleted, or replaced. Behind the scenes, Kubernetes keeps track of all the pods that belong to that service. When a request arrives, Kubernetes forwards it to one of the healthy pods available. This gives us three important benefits. First, a stable IP address. The service remains the same even when pods change. Second, a stable DNS name. Applications can use the service name instead of remembering IP addresses. And third, load balancing. Traffic is automatically distributed across multiple pods, helping the application scale and remain available. This is why services are one of the most important networking components in Kubernetes. At this point, you might be wondering something. How does a service know which pods belong to it? Kubernetes doesn't connect services to pods using IP addresses, and it doesn't connect them using pod names either. Instead, Kubernetes uses labels and selectors. A label is simply a key value pair attached to a pod. For example, a pod might have the label app equals Nginx. Then, inside the service definition, we create a selector that says, send traffic to every pod that has the label app equals Nginx. Kubernetes continuously watches the cluster and automatically matches pods to services based on those labels. This means that if a pod is deleted and a new pod is created with the same label, the service immediately starts routing traffic to the new pod. No manual updates are required. This dynamic discovery mechanism is one of the reasons Kubernetes networking is so powerful and scalable. In this example, the service selector is looking for pods with the label app and Nginx. Any pod that matches this label automatically becomes part of the service. We already know how a service finds pods, but how do applications find a service? Kubernetes solves this using built-in DNS. Whenever a service is created, Kubernetes automatically creates a DNS record for it inside the cluster. This means applications don't need to know IP addresses. Instead, they can communicate using simple names. In this example, the front-end application wants to reach the back-end service. Rather than calling an IP address, it simply uses the service name. Kubernetes DNS resolves that name to the correct service automatically. The full DNS name follows this format: service-name.namespace.svc.cluster.local. In our example, that's backend.default.svc.cluster.local. Most of the time, applications can simply use the service name, such as backend, and Kubernetes handles the rest. This is called service discovery, and it allows applications to communicate reliably without tracking changing IP addresses. Here we can see the different parts of the DNS name: the service name, the namespace, the service domain, and the cluster domain. Now that we understand how services provide stable networking and automatic discovery, let's look at the different types of services available in Kubernetes. We'll start with the most common one, ClusterIP. The first service type we'll look at is ClusterIP. This is the default service type in Kubernetes. In fact, if you create a service and don't specify a type, Kubernetes automatically creates a ClusterIP service. A ClusterIP service is only accessible from inside the cluster. Applications running outside Kubernetes cannot reach it directly. That's why it's commonly used for internal communication between services. For example, a front-end application might need to call a back-end API. Instead of connecting directly to individual pods, the front-end sends requests to a ClusterIP service. The service then routes traffic to one of the back-end pods available. This provides a stable endpoint while allowing pods to be created, deleted, or replaced without affecting the application. Because of this, ClusterIP is the most common service type in microservices architectures. Notice that the front-end application can reach the service because it's inside the cluster, but external users cannot access it directly. That's the key characteristic of ClusterIP, internal access only. Before we move to external access, there's one more concept worth understanding. Behind every service, Kubernetes maintains a list called Endpoints. These endpoints contain the real pod IP addresses currently receiving traffic. The service remains stable, but the endpoints list is updated automatically as pods are created or removed. This is how Kubernetes always knows where to route traffic. Now let's move beyond the cluster and see how applications are exposed to external users. So far, every service we've discussed has been focused on internal communication. Applications can talk to other applications, services can discover pods automatically, and Kubernetes keeps traffic flowing even as pods are created and destroyed. But there's one important question left. How do users outside the cluster access our applications? A customer opening a website doesn't live inside Kubernetes. A mobile app doesn't live inside Kubernetes. They need a way to reach services running inside the cluster. That's where Kubernetes service types like NodePort and LoadBalancer come in. They allow us to expose applications beyond the cluster boundary and make them accessible to external users. Let's start with NodePort. Until now, all the services we've discussed were only accessible from inside the cluster. NodePort changes that. A NodePort service exposes an application by opening a port on every node in the Kubernetes cluster. By default, Kubernetes uses ports in the range from 30,000 to 32,767. In this example, Kubernetes assigned port 30,080. Any request sent to a node's IP address on that port will be forwarded to the service and then routed to one of the pods behind it. This means external users can now reach the application from outside the cluster. The access pattern looks like this: node IP followed by the node port. Let's see what actually happens when a user accesses a NodePort service. The user sends a request to the IP address of any node in the cluster, followed by the node port. For example, node IP :30,080. Every node in the cluster listens on that same port. It doesn't matter which node receives the request. Kubernetes will forward the traffic to the service. The service then routes the request to one of the available pods. This means the application remains reachable even if pods move between nodes or new pods are created. From the user's perspective, they only need a node IP address and the node port. Kubernetes handles everything else behind the scenes. Notice that both nodes expose the same port. Even if the pod is running on a different node, Kubernetes can still route the request correctly. That's one of the advantages of the service abstraction. While NodePort works well for testing and learning Kubernetes, there is still a problem. Users need to know a node IP address and a custom port number. In production environments, we usually want a cleaner public endpoint. That's where LoadBalancer services come in. NodePort allows external access to an application, but users still need to know a node IP address and a custom port number. In cloud environments, Kubernetes provides a more convenient option called LoadBalancer. When we create a service of type LoadBalancer, Kubernetes asks the cloud provider to provision an external load balancer automatically. AWS, Azure, and Google Cloud all support this behavior. The cloud provider creates a public endpoint and connects it to our Kubernetes service. Users no longer need to know node IPs or node ports. They simply access the application through a public IP address or DNS name. Traffic is then distributed across the cluster and routed to healthy pods automatically. This is the most common way to expose production applications running in Kubernetes. Let's follow a request from the internet all the way to a pod and see how this works in practice. Here's the complete traffic flow. A user sends a request from the internet. The request first reaches the cloud load balancer. The load balancer forwards the request into the Kubernetes cluster. Kubernetes then routes the traffic through the service. Finally, the request reaches one of the available pods running the application. The user only sees a single public endpoint. Behind the scenes, Kubernetes and the cloud provider work together to distribute traffic across multiple nodes and pods. This provides scalability, high availability, and a much better experience than exposing individual nodes directly. That's why Load Balancer is the standard choice for production workloads in cloud environments. At this point, you might be wondering, which service type should I actually use? A simple way to think about it is by asking 3 questions. First, do applications only need to communicate inside the cluster? If the answer is yes, use ClusterIP. This is the default choice for internal microservice communication. Second, are you testing, learning Kubernetes, or running an on-premises cluster without a cloud load balancer? Then NodePort is often a good option. It provides external access through a node IP and port. Finally, are you exposing a real application to users on the internet? In most cloud environments, Load Balancer is the preferred solution. It provides a public endpoint and automatically distributes traffic across your application. As a general rule, ClusterIP for internal traffic, NodePort for labs and on-premises environments, Load Balancer for production workloads. Now that we understand when to use each service type, let's create some services ourselves and see these concepts in action. We've covered the theory. Now let's create our first Kubernetes service and see how Kubernetes connects a service to a running pod. Let's create a dedicated folder for this demo and keep our manifest organized. To save some time, I already have a deployment manifest prepared from a previous example. Let's quickly review it before we deploy it. This deployment creates 3 replicas of an Nginx application. Here we can see the image we're using, which is the official Nginx image. We can also see the replica count set to 3, meaning Kubernetes will keep 3 pods running at all times. But the most important part for today's lesson is this label, app equals Nginx. Remember this label because our service will use it later to discover these pods automatically. The selector and the pod template labels must match, otherwise the deployment wouldn't know which pods belong to it. Everything looks good, so let's deploy it. Kubernetes is now creating the deployment and the pods for us. Let's verify that everything is running correctly. Perfect. We now have 3 Nginx pods running in the cluster. At this point, the pods exist, but there is no service in front of them yet. Let's create one and see how Kubernetes connects everything together automatically. Just like the deployment, I also have a service manifest prepared. Before we create the service, let's take a closer look at these 2 manifests. On the left, we have our deployment. This deployment creates 3 Nginx pods, and each pod receives the label app equals Nginx. Now look at the service on the right. The service has a selector that is also looking for app equals Nginx. This is how Kubernetes connects services to pods. The service doesn't know pod names. The service doesn't track pod IP addresses. It simply looks for pods that match its selector. In our case, every pod created by this deployment has the label app equals Nginx, so all of them will automatically become part of the service. This is one of the most powerful concepts in Kubernetes. Services and pods are connected dynamically through labels and selectors. One more thing before we create the service. Notice that the service type is set to ClusterIP. That means this service won't be accessible from the internet. For this demo, that's exactly what we want because we're focusing on how services discover and connect to pods. Now let's create the service. Let's verify it. Perfect. We can now see our service running in the cluster. Notice that its type is ClusterIP, exactly as we defined in the manifest. Kubernetes also assigned a ClusterIP automatically. This is the stable virtual address applications inside the cluster we'll use to reach our service. Another interesting detail is that we can also see a service called Kubernetes. This service is created automatically by Kubernetes and is used internally by cluster components to communicate with the Kubernetes API server. The important one for our demo is Nginx-service. Let's see which pods are currently behind it. So far, we've seen the service and its cluster IP, but how does the service know where to send traffic? To answer that, let's look at the endpoints associated with this service. Perfect. This command shows the endpoints associated with our service. Notice that we have 3 IP addresses listed here. These are not service IPs. These are the actual IP addresses of the pods currently backing the service. Earlier, Kubernetes assigned a single cluster IP to the service, but when traffic reaches that service, Kubernetes needs to know where to send it. That's exactly what the endpoints list is for. Kubernetes automatically discovered all 3 pods because they match the selector app equals Nginx. Then it added their IP addresses to the endpoints list. This means the service acts as a stable front door, while these pods are the real destinations receiving the traffic. And the best part is that this list is maintained automatically by Kubernetes. Let's prove that. If Kubernetes is managing these endpoints automatically, what happens when one of the pods disappears? Let's delete one and find out. Notice what just happened? We deleted one of the pods from the deployment. A few seconds later, Kubernetes automatically created a replacement pod to maintain the desired state of 3 replicas. Using the wide output, we can see the pod IP addresses. The new pod now has the IP address 10.244.0.19. The previous pod IP no longer exists. This is exactly the problem we discussed earlier in the episode. Now let's check the service endpoints again. Notice that Kubernetes automatically removed the old pod IP address and added the new one. Earlier, the endpoints list contained, after recreating the pod, Kubernetes updated the list automatically. The service didn't change, the cluster IP didn't change, only the endpoints changed behind the scenes. What happens if all the pods disappear? Let's delete the deployment and see what happens to the service. Remember, our service currently has the cluster IP 10.105.10.112. Now let's remove all the pods behind the service. Notice that the service still exists and the cluster IP has not changed. The service remains available even though there are no pods behind it. The service still exists, but there are currently no endpoints. Kubernetes has nowhere to send traffic. Let's bring the application back. Notice that Kubernetes created completely new pods. They have different names and different IP addresses. Kubernetes automatically discovered the new pods and updated the endpoints list, and our service still has the exact same cluster IP. We never recreated it. We never modified it. Kubernetes simply reconnected it to the new pods. Instead of connecting to a pod IP, we're connecting to the service. The service doesn't care which pods are currently running. Kubernetes automatically routes traffic to the available pods. The pods changed. The pod IPs changed, the endpoints changed, but the service remained exactly the same. That's why applications communicate through services instead of pod IP addresses. Perfect. The application is responding through the service, but let's perform another test. Earlier in the episode, we learned that pods are not permanent. Kubernetes can delete and recreate them at any time. So what happens if one of the pods disappears? Will the application stop working? Let's find out. Let's delete one of them. Notice that the deployment immediately created a replacement pod. We still have 3 replicas running, and the application is still responding. We deleted a pod, but the service continued working without any changes. That's because Kubernetes automatically routed traffic to the remaining healthy pods while the replacement pod was being created. If we look at the endpoints, we can see that Kubernetes automatically updated the list of pods behind the service. This happened without any manual configuration. And that's the real value of Kubernetes services. Applications don't need to track pod names. Applications don't need to track pod IP addresses. They simply communicate with the service. Kubernetes takes care of discovering pods, updating endpoints, and routing traffic automatically. This makes applications more reliable, scalable, and resilient to change. In this episode, we learned what Kubernetes services are, how they discover pods using labels and selectors, how service discovery works through DNS, and when to use ClusterIP, NodePort, and LoadBalancer. We also created our own service and saw Kubernetes automatically update its endpoints when a pod was replaced. In the next episode, we'll continue building our Kubernetes knowledge with another hands-on example. Thanks for watching, and see you in the next one.